Hello everyone, welcome to Big Boy Physics, and today in this video we'll be talking about the topic of atomic collisions. Well, you can see that it's very confidential and all those stuffs are given, so that's just written in the thumbnail. And today we'll be discussing the detailed theory regarding the concept of atomic collisions and what is Q value, kinetic energy of the targeting particle, what is how the targeted particle gains the energy in form of Q value due to the loss in energy due to the collisions. Okay, so these are the topics which we'll be discussing in this video. So let's get started. First, we'll be knowing about some term known as excitation. Now, what happens during collision? Let me explain. You must have remembered about James Chadwick experiment that bombarding alpha particles on beryllium nucleus. Okay, so there's some beryllium nucleus and alpha particles are emitted which strikes the beryllium nucleus. Then it gives a, probably you may know, it gives carbon and a neutron is given out of the reaction. Okay, so basically this was the James Chadwick experiment, and this explained that how neutrons are produced and proved the existence of neutrons inside the nucleus. Okay, so this is a very important, significant experiment which proved the existence of neutron. Now you might be wondering how much this reaction occurred. Did this reaction cost some energy? Yeah, of course it must have costed some energy. Suppose it's Q. Well, from Einstein's theory of energy mass relation, we write Q is equals to mass of. I'm writing the nuclear masses here. Okay, even if you write atomic masses, this won't be any problem because these are, it is an alpha decay, alpha particle is involved, so generally the mass of electron does not come in the consideration. So Q value is written as mass of alpha plus mass of beryllium minus mass of carbon minus mass of neutron into c square, as c is the speed of light, and m, alpha, me, mc and mn all are in written in kg, or you can even write in AMU and convert it into energy mass relation, whatever you do. Okay, so this is the energy, or you can say this has the threshold energy, means minimum to minimum this energy is required to proceed the reaction. Now for now let's assume that the beryllium nucleus is at rest. Okay, so beryllium nucleus is at rest and alpha particle is getting bombarded. Something this is happening like you are charging a bullet. This orange color dot is alpha particle and you are charging a bullet onto you can say this big fat metallic sphere. This is beryllium. Okay, this bullet gets charged to this beryllium and impinges this beryllium. This result in formation of a carbon and a neutron. Suppose these two move with same energy. Now, can you tell me the maximum loss which can be produced? And you know that maximum loss is produced when the collision is perfectly inelastic or perfectly plastic, whatever you say. So, what is the maximum energy loss? E loss max is equal to mass of beryllium, or you can write this mt, that is the mass of the targeted particle, or let this mass be capital M and this mass be m alpha. So I can write maximum loss as half mu v square, since velocity of center of mass is same. So half total mass into vcm square is constant, but this factor will be missing in the second term, second case, that is when the collision is complete. But in the first case there will be some half mu v square factor, so that will be the maximum loss produced. You can write it to be half m alpha into capital M by m alpha plus m into v square, where v is the relative velocity. Now observe this alpha particle and beryllium particle. Beryllium particle is at rest, that is v is equals to 0, and alpha particle is moving with v is equals to v. So v relative will be just the velocity of the alpha particle. Another thing to observe that k, that is the kinetic energy of the targeting particle, is equals to half m alpha v square, right? So you can say that loss max is equal to capital M times K by M alpha plus M. and that's the maximum loss we can be produced in energy. This is equals to the Q value. Writing kinetic energy in terms of Q value, you'll get 1 plus small m alpha by capital M, and that's the answer. Basically, this is the relation between the kinetic energy to be given to the alpha particle to produce the reaction or make the reaction fruitful. Well, observe one thing, that the kinetic energy is actually more than that of the Q value. Since this term is positive, the ratio is positive, 1 plus m alpha by capital M. So the kinetic energy required is more. This is an important thing to observe. If you write m alpha, all those, so just for some plan, m alpha is 4 by, and mass of beryllium is 9, so you'll get 13 by 9 into Q, and that's the kinetic energy required. So we have basically discussed this in terms of a nuclear reaction. Can you tell me some other cases in which we can observe? Yeah, of course. Suppose I am targeting a particle, suppose a proton only. It's a proton, and it's getting targeted on a hydrogen. Now, it can either form deuterium, but I don't know whether deuterium will form, because will the reaction be feasible or not. I don't have that idea. Or you can assume another hydrogen itself. Okay. Now these two combines to form deuterium. Or another case is something like hitting with a neutron. Then neutron and hydrogen moves, but they are moving with same velocity. I'm considering this reaction. Suppose this does not involve any nuclear reaction, which leads to the formation of deuteron or deuterium, whatever you say, or let it be some particle K. I don't know this particle. Which particle is this? And later, these two particles are found to move with same velocity. Initially, hydrogen is at rest. Okay, so these two particles starts to move with same velocity. Then what? Where did the loss go? Where did the loss go? The loss can be transferred into excitation. We know that a hydrogen atom consists of various energy levels. Suppose initially the electron is at ground state, then finally it went to the fourth state. Okay, for that you need energy 13.6 into 1 minus 1 by 4 square. Thus, for excitation in hydrogen atom, you can say that the energy required should be quantized. It should be 13.6 into 1 minus 1 by 4 square. Better not to use the word quantized or some fixed values. Only some fixed value can lead in the excitation. Now suppose you want to excite the electron to the second step. What is the energy? Q value of the reaction will be 13.6 into 1 minus 1 by 4. That is 1 minus 1 by 2 square. If you find the value, it will get 10.2 electron volts. Now one thing I can say you that the kinetic energy is basically mass of the targeting particle upon mass of hydrogen plus 1 into 10.2. This is the kinetic energy of the targeting particle required. Tell me one thing. Is this the minimum kinetic energy, or this much kinetic energy is required? Think a bit. Well, you can use a particle with more than kinetic energy. What will happen in that case? That it will be a partly plastic collision. In a partly plastic inelastic or inelastic collision, the velocities will not be same. Rather, they will be different, but there will be some loss in kinetic energy. We can say there will be some kind of loss. That is why there will be some kinetic energy of the targeting particle. If you keep it more, then there will be some loss, but it will not be perfectly plastic. Okay, so just do whatever you want. Now third case is a little interesting. We'll be talking about gamma decay. You'll be wondering what is there in this. Okay, we'll be doing a pathfinder problem from this also. Just go with the flow. Suppose I have a particle of mass capital M, and now in a later time t, this decays into the same particle of mass M, and the thing is that it emits a gamma photon. Okay, it emits a gamma photon, and the particle remains same. Can you tell me that why did the particle, what was the intention of the particle to emit the gamma photon? read NCRT, in NCRT class 12 part 2, it's given clearly that nucleons also have discrete energy states. Okay. Now nucleus has discrete energy states. Suppose this is state 1 and state 2. Now when energy gets emitted, the it jumps from, suppose this is state 1 and state 2, then it jumps from state 2 to state 1, and due to the decreasement in energy, gamma photon is evolved or produced. Now let the rest mass energy of this particle to be E naught and the energy of the gamma photon to be E. So I can say that initial energy, and if this is the bandwidth or the gap between the transitional energy states, means the energy states between which the transition occurs. So I can say that if this is 0, this is W. So I can say E naught plus W is equals to under root PC whole square plus E naught square plus E. You'll be wondering what is this term. Let me explain. Suppose you have a particle and this particle moves with velocity v. We know that due to energy mass relation, we can say rest mass energy m naught c square, where m naught is the rest mass. You must know that mass can be written as m naught by m naught gamma, where gamma is also called the Lorentz factor. Okay, when the particle moves with some velocity, then the mass increases by the factor of Lorentz factor, which is given as m naught by under root 1 minus v square by c square. Okay. Now what we say that if velocities are not relativistic, we write total energy to be m naught c square plus half mg square. This is the kinetic energy term. This is the potential. This is the rest mass energy term. Now, if velocities are relativistic, you write energy to be m naught c square whole square plus p into c whole square, where p is the momentum of the particle. P is the momentum of the particle into the light speed whole square plus m naught c square whole square, and this is the energy of the particle. So that's all the thing we have written here, and Pc, that is basically momentum, is given as E by C is equals to P. So Pc can be written as E, and we can finally substitute E in this case. Hence I can say that the width between, that is the gap between the two states, is given as under root E square plus E naught square plus E minus E naught, right? Can you tell me that if I don't consider this approximation also, will I, if I consider the approximation instead of considering the result, exact result, will I get the same value? Well, yeah, in few cases you will get, because generally E is much less than E naught. So I can say that this E plus E naught square, I can use binomial approximation, or just consider something like this: E naught plus W is equals to E naught plus what is the energy of this particle. This will have some momentum p square by c, p square by 2m. You'll get e square by 2m c square, e square by 2m c square, where m o is better to write, that is m naught, in a rest mass, plus e. Okay, so from here we'll get an interesting result, like m naught c square is given as e naught, so write it e naught. W is equal to e square by 2 e naught plus e, and that's the interesting result I'm talking about. Now consider this photon to fall on this another nucleus, the same nucleus, that is of same, having same rest energy. Initially, suppose this was tin nuclei, and this tin nuclei gave some gamma photon. It recoiled. Now this gamma photon is hitting another tin nuclei. So, and I need to find the velocity so that transition is possible. Okay. Now this tin nuclei gets hit. Now what will happen, that now in this case nuclear excitation will jump from 1 to 2. So I can say that initially the energy is E, is the energy of photon, plus half mv square, or you can write p square by 2c, 2m naught. is equals to W. Now this energy transition occurs W plus P minus E by C whole square upon 2m naught. So basically this will be the new momentum. What will happen by momentum conservation, and we assume that this velocity to be in the opposite direction to the photon. So initial momentum is p. Now p is equals to p dash, p minus e by c is equals to p dash. So p dash is equals to p minus e by c. This will be the kinetic energy in the later case. If we consider the further equation evaluation, w is written as e square by 2 e naught plus e naught square by e square by 2 e naught plus e, and cancelling the terms, and using a minus b into a plus b is equals to a square minus b square, we'll get e by c into 2p minus e by c upon 2m naught is equals to e square by 2 e naught. Now m naught e naught is written as m naught c square. Cancelling all the irrelevant terms, e c all those, you will get 2p is equals to 2e by c. So I can write that the momentum of the particle required is e by c. Hence, velocity is written as e by m naught c, and that is the velocity required for the thin nucleus to undergo the excitation, so that when the gamma photon is uh, emitted and it strikes the nucleus, it can go the required excitation. Okay. Basically, the thin nuclei must have this threshold energy, threshold velocity, you can say, to undergo excitation. Just a minute, I'll be showing you some surprise. Okay, so this is the extract of the page of Pathfinder Modern Physics. Just read question number 13. The question number 13 says a free motionless nucleus of tin 119 SN emits a gamma photon of energy 22.6 and blah blah blah. And they are saying the rest energy is 113 giga electron volts. So if you observe, we just solved Pathfinder question number 13. Okay, we just solved Pathfinder question number 13 without even any indication. We just discussed the relevant theory and all those. Well, when I was evaluating, considering the relativistic limits, then I was getting a very dirty quadratic. But when I observed that this thin nuclei rest energies of giga electron volts is much larger than the energy of the photon emitted, and if you even consider the light speed limitation, then also you'll get the energy due to kinetic, that is Pc. 1 minute, yeah, Pc would be much less than E naught. This is one thing you'll be getting while doing. So you can finally use binomial approximation and all those stuff to find the resulting answer. If you put the value E by m naught c, you will get 22.6 into 10 to the power 3 into 1.6 times 10 to the power minus 19 by c is 3 times 10 to the power 8, and mass is 119 into 1.6 times 10 to the power minus 27, basically 1.67, right? And you know that 3 into 1.67 is 5 almost. Just I'm using a little bit of calculator. It's 10 to the power minus 16, and this is 10 to the power minus 19. You'll get 10 to the power 3. So you'll get something answer like 60, I guess. 119 divided by 5 into 1000. Yeah, the answer will come out to be nearly 60.773, or nearly 60. Answer is given as 60 meter per second. So yeah, that's pretty likely to get to be the answer to this problem. So we just unknowingly, or without an indication, solved question number 13 of Pathfinder. Now considering question number 14 once, when an alpha particle collides with a stationary lithium nucleus, the nuclear reaction takes place. The Q value of this reaction is this, find the minimum value of the kinetic energy. Very simple. The targeting nucleus mass is 4, 1 plus 4 by 7 into 2.87 for question number 14. This will be the kinetic energy required. We know that the kinetic energy required is always more than the Q value, so you can just memorize like this. The kinetic energy required is more, so it will be multiplied by a factor of mass of the targeting nucleus, for here it's alpha particle, upon mass of the targeted nucleus into Q value, and that will be the answer. So you will get something like 11 divided by 7 into 2.87, and final answer will come out to be 4.51 electron volts. And whatever the units are used, so it will be mega electron volt. Okay, and that's the answer to the question number 14 according to me. Let me check it once. Yeah, that's the answer. And they're saying that the Q value of the reaction is minus 2.87 mega electron volt. What it means, basically, that when the particle is projected, what will happen that energy will be released or absorbed, and the reaction will be proceed as per Q value is given as mass of reactants minus mass of products into C square. This implies that the mass of the reactants will be more than the mass of the mass of the reactants will be less than the mass of products. It implies basically it's an endothermic reaction. Okay. So if since Q value is negative, it means that energy will be absorbed. Yeah, it makes sense. If the Q value is positive, it means the reaction is spontaneous. Then there will be zero kinetic energy needed for the helium nucleus to be targeted. Q value was positive. Since Q value is negative, that is why we need to eject some energy, which will be inculcated by the loss, and that will come in form of Q value. So we are done with question number 14. Coming up with question number 15. Question number 15 is also same, but it does not involve any formula. You need to just use basic concept of mechanics. It says that there's a deuterium tritium fuse according to the reaction, and you have to tell me the value of the kinetic energies carried by neutron and the alpha particle. Well, you know that momentum should be same. Momentum of alpha particle will be momentum of neutron. So kinetic energy of alpha particle is to kinetic energy of neutron will be distributed in the inverse ratio of masses. 1 by 4 is to 1 by 1. You'll get 1 is to 4. So kinetic energy of alpha will be 1 by 5th of the Q value. And this is a spontaneous reaction. Observe that this is a spontaneous reaction. Why? Let us check. Q value will come out to be 1 times 1 times all those 1 times 2 plus 3 times 2.8. Wait, now observe one thing, that these are given as the binding energies. Okay, now in case of binding energy, what will happen, let me explain. Here is deuterium, here is tritium. For deuterium it's given that binding energy per nucleon is 1 mega electron volt, and for tritium it's 2.8 mega electron volt. Now there are two nucleons in deuterium, so what will be the energy you need to give so that it splits into proton plus neutron? Similarly for tritium, so the energy you need to give is plus 2.2 times 1, and for tritium is 3 times 2.8, and these two particles combine to give some new particle which is given as helium. So for formation of helium, how much energy is to be liberated? Minus 7 times 4. Okay. Now doing all the calculation, you get 20 the energy liberated. So energy liberated is equals to negative of 2.8 into 3 is 7.4 8.4 plus 2 minus 28, and doing some more calculation, 28 minus 8.4 minus 2 will get it to be 17.6. So energy liberated will be 17.6. Now this energy liberated will go into the kinetic energy of alpha particle and the neutron. For kinetic energy of alpha particle will be 1 by 5th of 17.6. You'll get 5 3s are 15.3 3.52 SI units, and this should be 3.52 mega electron volt. So the kinetic energy of the alpha particle is found to be 3.52 mega electron volts. And for neutron, it will just subtract or multiply with 4 by 5th. You will get the answer, kinetic energy of the neutron to be 14.08 mega electron volt. And that's the answer to the given problem. Hope you enjoyed this video and learned something new. Thank you and have a nice day.